And there is one new technique, and that one new non-testable technique is called state space. The number one way that they analyze systems in grad school is in the first month, they'll be doing the same things we're doing now, but after that, they use state space. What is it? It's like a differential equation, but it has multiple inputs and outputs. And in order to handle those multiple inputs and outputs, it's a very general method. It has any number of inputs, any number of simultaneous outputs. And so it uses matrices. And in particular, just so you've seen it once, the standard, just like in difference equations, the standard input is X. Using state space, Z is the standard input. And now it's a vector. You can have, if it's a length 3 input vector, then you've got 3 different simultaneous inputs. Z sub 1 of t, Z sub 2 of t, Z sub 3 of t. Y is an output vector. And it can have a different dimensionality than your number of inputs. You might have 17 outputs. Just like tax policy probably affects at least 17 different markers of economic growth. X is something brand new. X is a state vector. And what I want you to think of about states is it's the same thing as what we might call initial conditions, except it can vary with time. Instead of it just being initial, it's the current condition. So it'd be the voltage across a capacitor, or the currents through an inductor. Those are examples of state vectors. Then this is the derivative, the first derivative of your state vector. So in a complex circuit that has 3 inputs, 4 outputs, and 6 capacitors, 3 inputs, your input vector would be of length 3. 7 outputs, your y vector would be length 7. And if it had, I don't remember how many capacitors I said, if it had 5 capacitors, your state vector and the derivative of the state vector would both be length of 5. And then you've got 4 coefficient matrices, and those coefficient matrices are the things that actually describe what the heck the system does, and they are all related by saying that the derivative, the first derivative of your state vector, is equal to some combination of your current state vector plus some combination of your input. And then your output, which is obviously what you eventually want to find, is some combination of your X vector plus a different combination of your, so some combination of your state vector plus a different combination of your input vector. And then to find your updated X vector a moment later, you have to find it's a function of your derivative. So these are the 2 equations that form the state space formulation of a system. And why do we do this pain? 2 reasons. First, it's the only elegant formulation for multiple input, multiple output systems. MIMO. In this course, in all undergraduate courses, they only cover SISO, single input, single output systems. But secondly, the matrices that they use lend themselves to computer analysis. Because ultimately, you don't want to be doing anything by hand. You want to just feed it into a computer and let the computer run with it. So all that I want you to get out of this class is that there is this analysis method that's used, that's heavily weighted commonly in graduate schools, but you will touch on it in future classes in electrical engineering as an undergraduate. It's not DSP, but in courses in communications theory, certainly, or controls theory. In controls theory with Colonel Feinauer, you will touch on state space formulations. But really what I want you to know is that the primary system representations for single input, single output systems like we're going to cover are the schematic representation, the transfer function, which is at its core, and then be able to translate from circuit to transfer function, and then from transfer function to any mixture of impulse, differential equation, and S-plane, and be able to go from any of those back to the transfer function.